Radiation is a ubiquitous phenomenon in the world of physics, encompassing all forms of electromagnetic waves, particles, and energy. From medical imaging to astrophysics, the study of radiation and its properties has played a crucial role in our understanding of the world around us. In this lecture, we will explore the fascinating world of radiation sources and detectors and their significance in optical instruments. We will begin by examining the fundamental principles of radiation, its various forms, and its importance in the field of physics. From there, we will delve into the different types of radiation sources and detectors used in optical instruments. We will discuss the natural and artificial sources of radiation, their characteristics, and their applications. Then, we will explore the different types of radiation detectors, including their working principles and characteristics. Finally, we will discuss the importance of radiation sources and detectors in optical instruments, looking at examples of instruments that utilize these components, including spectrometers, microscopes, and telescopes. Natural sources of radiation are all around us and have been present since the beginning of time. These sources of radiation include cosmic rays, which are high-energy particles that originate from outside our solar system. They are primarily composed of protons and other atomic nuclei. These particles collide with the Earth's atmosphere, creating a shower of secondary particles that contribute to the natural background radiation. Terrestrial radiation includes naturally occurring radioactive isotopes found in the Earth's crust, such as uranium, thorium, and potassium. These isotopes decay over time and release alpha, beta, and gamma radiation. Radon gas is a colorless, odorless, and tasteless gas that is formed from the decay of uranium and thorium in the Earth's crust. Radon is the leading cause of lung cancer among non-smokers and can accumulate in buildings if not properly ventilated. The sun is a significant source of radiation, emitting a wide range of electromagnetic waves, including ultraviolet, visible, and infrared light. These natural sources of radiation contribute to the background radiation that we are all exposed to on a daily basis. While the level of exposure to natural radiation is generally low, it can vary depending on location and other factors. Understanding the characteristics and sources of natural radiation is critical for a broad range of applications, from space exploration to medical imaging. Artificial sources of radiation are created by human activities and include X-ray and gamma-ray machines, which are widely used in medicine, industry, and research to generate high-energy radiation for various purposes, such as medical imaging and material testing. Nuclear power plants generate electricity by harnessing the energy released by nuclear reactions, which produce large amounts of radiation in the form of alpha, beta, and gamma particles. Radioactive isotopes are artificially produced in nuclear reactors or particle accelerators and have many practical applications, such as medical imaging and cancer treatment. Nuclear weapons are devices that utilize nuclear reactions to produce large amounts of energy and radiation, with devastating consequences if used in warfare. While artificial sources of radiation can be powerful tools for many applications, they can also pose significant risks to human health and the environment if not handled properly. Understanding the properties and characteristics of artificial sources of radiation is critical for ensuring the safety of workers, the public, and the environment. Radiation sources can be characterized by several factors, including energy, intensity, half-life, type of radiation, and stability. The energy of a radiation source refers to the amount of energy released per unit of mass. High-energy sources, such as gamma rays, can penetrate deep into materials and tissues, while low-energy sources, such as alpha particles, have a limited range and are easily absorbed. Intensity refers to the rate at which radiation is emitted. A high-intensity source will emit more radiation than a low-intensity source. The half-life of a radiation source refers to the time it takes for half of the radioactive isotopes to decay. This factor is crucial for understanding the decay characteristics of a source and how long it will remain radioactive. Radiation can take different forms, including alpha, beta, gamma, and neutron radiation, each with different characteristics, such as range and ability to penetrate materials. The stability of a radiation source refers to how well it maintains its radioactive properties over time. Some sources may decay quickly and lose their radioactive properties, while others may remain stable for thousands of years. Radiation detectors are used to measure and detect radiation from both natural and artificial sources. There are several types of radiation detectors, including Geiger-Müller (GM) counters, which are one of the most widely used types of radiation detectors. They operate by using a gas-filled tube that ionizes the gas when radiation passes through it, creating a pulse of electrical current that can be measured and counted. Scintillation detectors use materials that emit light when exposed to radiation. The emitted light can be detected and measured to determine the presence and intensity of the radiation. Semiconductor detectors use materials such as silicon or germanium to detect radiation. When radiation interacts with the detector, it creates an electrical charge that can be measured to determine the presence and intensity of the radiation. Ionization chambers use a gas-filled chamber to measure the ionization caused by radiation passing through the chamber. The ionization creates a current that can be measured and used to determine the presence and intensity of the radiation. Film badges are a type of dosimeter that use photographic film to detect and measure radiation exposure. The film is exposed to radiation and then developed to produce an image that can be analyzed to determine the level of exposure. Each type of radiation detector has its advantages and limitations, and the appropriate detector for a given application depends on various factors, such as the type and energy of the radiation and the required sensitivity and accuracy. Radiation detectors operate based on the interaction of radiation with matter. When radiation passes through a material, it may ionize atoms or molecules in the material, transfer energy to electrons, or cause the emission of photons or electrons. Radiation detectors are designed to detect and measure these interactions and provide information on the presence and intensity of the radiation. The key characteristics of radiation detectors include sensitivity, which refers to the minimum amount of radiation that a detector can detect; resolution, which refers to the ability of a detector to distinguish between different levels of radiation; efficiency, which refers to the percentage of radiation that a detector can detect; response time, which refers to the time it takes for a detector to respond to changes in radiation levels; and linearity, which refers to the ability of a detector to provide a proportional response to varying levels of radiation. Radiation sources and detectors play a critical role in various optical instruments, including spectrometers, microscopes, and telescopes. These instruments rely on radiation sources and detectors to analyze, measure, and visualize various optical properties of materials and objects. Spectrometers are used to analyze the spectral properties of materials and light sources. They typically use radiation sources, such as lamps or lasers, to provide a source of radiation, and detectors, such as photomultiplier tubes or CCDs, to measure the intensity of the radiation at different wavelengths. Microscopes are used to visualize and analyze small objects and structures. They use radiation sources, such as light sources or lasers, to illuminate the object, and detectors, such as photomultiplier tubes or CCDs, to capture and analyze the images. Telescopes are used to observe and study objects in the sky. They use radiation sources, such as stars or galaxies, as the source of radiation, and detectors, such as CCDs or photomultiplier tubes, to capture and analyze the images. Radiation sources and detectors are essential components of these instruments, providing the necessary information to analyze and visualize the optical properties of materials and objects. Without these sources and detectors, many optical instruments would be unable to function effectively. Current research and developments in radiation sources and detectors are focused on improving their sensitivity, resolution, and accuracy. For example, researchers are developing new types of radiation detectors with higher sensitivity and resolution, such as superconducting detectors and quantum detectors. Additionally, there is ongoing research on developing new techniques for using radiation sources and detectors, such as multimodal imaging and hyperspectral imaging, to enhance the capabilities of optical instruments. In conclusion, radiation sources and detectors are critical components of many optical instruments, providing essential information for analyzing and visualizing the optical properties of materials and objects. Ongoing research and developments in this field are aimed at improving the sensitivity, resolution, and accuracy of these instruments, opening up new possibilities for optical research and applications.